Hi, my name is John. Today I'll be presenting MapReduce, Simplified Data Processing on Large Clusters by Jeffrey Dean and Sanjay Gamawat. This was originally presented in the 6th Annual Symposium on Operating System Design and Implementation in 2004. As we know, parallel applications are becoming more and more prevalent in today's computing environment. In this paper, the authors note that many of the applications at Google, although they all operate over the same cloud infrastructure and accomplish essentially the same tasks, are developed independently and as a result end up having much duplicate code between each of the applications. And these applications serve special purposes only. So the authors propose several units of basic functionality that each of these applications share, specifically parallelizing the computation throughout the cloud infrastructure, dynamically balancing loads by distributing data to different nodes in the cloud, and effectively handling failures in the cloud without actually costing any impacting performance. So they noticed that in their source code tree at Google that the boilerplate code to accomplish each of these tasks is effectively the same in each application. To address this problem, the authors introduce a new programming model called MapReduce. MapReduce automatically parallelizes data throughout a cloud infrastructure as generic enough to be used for a wide variety of applications, including many of those in use at Google, and is scalable to extremely large data sets, as we'll see later in the paper. The only requirement on the data sets is that the input and output values and intermediate values be oriented as key value pairs. As the authors will show later, their implementation at Google relies on a commodity clusters, which is essentially a low cost and inherently lower quality cluster of machines. And even in this unreliable cluster, MapReduce is shown to perform very well. The author's main contribution through this paper is the MapReduce programming model itself, specifically the automatic parallelization and load distribution aspects of it, as well as the evidence of high performance even on a commodity cluster such as that at Google. So first I'll go through a variety of applications that can be easily generalized to the MapReduce programming model, specific details in the implementation at Google, a list of refinements that can allow more fine-grained control over the MapReduce model, and finally, an in-depth performance analysis of 2 example applications at Google. The MapReduce programming model itself is actually quite simple, built into 2 stages called map and reduce. Map happens first, and the input to the map stage is the input of the entire problem, and likewise, the output of the reduce stage is the output of the entire problem. The data is transmit in what we'll call the intermediate format from the end of the map stage to the beginning of the reduce stage. Another key feature of the data here is that it's all stored in key value pairs, and so all the data in both stages is accessed using its key, a unique key that we assign in the intermediate format and a unique key that we assign in the input format. Likewise, in the reduce stage, we use an iterator to access values from the intermediate format, and this allows us to have intermediate data that's much larger than whatever we can fit into memory on the machine running the reduce stage. So to the right you can see a code snippet representing a simple word counting application. So in the map stage we actually take in a key, which is a document name, and a value, which is the actual contents of the document. So we iterate through the words in that document, and for simplicity we just assume that each word occurs once. So we count, we assign a value of 1 to the key, which is the word in this case, for our intermediate format. Then from the reduce stage, like I said, the key in this stage is the word that we assign in the map stage. And so each reduce will be in charge of counting the occurrences of a specific word. And so you can see we just iterate through the counts in each document of the occurrences of a particular word and emit the result of the total number of counts in the body documents for this particular word. Since the MapReduce programming model is so general and only requires that the data be structured in key value formats, you can imagine this is a wide variety of applications. From a simple word index, like something we just saw that emits word document ID pairs and then sums the total number of occurrences for each word. We can also extend it to do a distributed grep function, which you could imagine simply takes the map function to emit each line that matches a particular pattern given to grep, and the reduce function would simply need to copy the line to output. Likewise, we can extend this to do a distributed sort function, and this relies specifically on the implementation choice to have the intermediate keys be given to the reduce function in a sorted order. And if we make that design choice, then this becomes a very simple application of MapReduce. In the map function, we simply need to emit key record pairs, and in the reduce function, emit each pair unchanged, because we know that we've already sorted the entire intermediate data set by its key. This diagram gives a nice overview of the MapReduce programming model architecture, so I'll go over each component individually to make sure you understand exactly how the whole system fits together. First, let's take a look at the master node. This master node is responsible for things like load balancing and assigning tasks to particular worker nodes. Specifically, it's responsible for assigning map tasks to map workers, and likewise the reduce tasks to reduce workers, as well as monitoring the progress of each of these tasks and helping optimize for efficiency. So first, let's start with the input files on the far left. These input files are split according to their keys, and each set of keys is sent to its corresponding map worker, and that map worker will do whatever computation it needs to and store the output of the map task, which is the intermediate data, locally at its machine on its hard drive. Once it's done that, it will contact the master node, and that master node will assign a worker the corresponding reduce task, and once that reduce task has completed, it will output its final data, the final data for the entire MapReduce application. One key thing to note here is that although it may appear as though the map tasks and reduce tasks are performed on different machines, it's often the case that the master node will actually assign a map task and its corresponding reduce task to the same machine. And this is to optimize for localities, you might imagine, since the map task will output the intermediate data to its local disk. And if the reduce task is run on the same machine, it only needs to access local disk instead of accessing another machine over the network. In the case that the reduce worker does need to access another machine over the network, it will actually do so by contacting the map worker over the network using the Google file system and retrieve the data, while the map worker might be working on something entirely different. To start off with our more in-depth analysis of Google's implementation of MapReduce, we'll first look at the hardware implications. As I said before, MapReduce in Google is typically run over commodity clusters. This means large clusters ranging from hundreds to thousands of machines, and commodity machines, meaning that these are nothing particularly special in terms of high computing. Each machine is typically dual-core, dual-processor x86 machines, ranging from 2 to 4 gigabytes of memory, typically with commodity networking cards with 100 megabits per second or 1 gigabits per second network speed, all connected by Ethernet, obviously, and using inexpensive IDE disks, typically 2 in RAID for redundancy. Likewise, the Google file system, which is demonstrated more in depth in a different paper, handles replication and reliability over this file system, because as you imagine, many of these machines do fail quite often. So as I mentioned before, in terms of the implementation architecture, we really have two main roles in the system. First, the master node, and second, the worker node. In terms of the master node, this node is in charge of things like keeping track of the state of different tasks, whether they be waiting to execute, currently executing on some worker machine, or completely finished with execution and waiting for others to finish. Likewise, it keeps track of which tasks are being executed on which worker machines and the location of these machines and how to contact them, as well as propagating the output file from the map stage to the beginning of the reduce stage. Likewise, the refinements that I mentioned before of the MapReduce programming model often happen at the level of the master node. In terms of the worker node, it simply performs a single map or reduce task. And although, as I said, the map and reduce task can happen on the same machine, we can conceptually think of a worker node as only performing one or the other. Since the MapReduce programming model is intended to be run on a commodity cluster, and we do have a large number of worker nodes, we assume that worker failure can be quite common. To deal with this, we have the master node pinging each of the workers intermittently and take one of several actions if we ever detect that one of the workers has failed. If a worker fails that has incomplete work on it, then we do need to actually start this whatever task over again on some other correctly functioning node, whether it be a map or reduce task. Likewise, in the event that a map task has completed and then that corresponding node has failed, we still need to rerun that map task again so that the corresponding reduce task can access the intermediate data it needs. However, in the event that a reduce task completes and then the corresponding node fails, we actually don't need to rerun any computation because we already have the final output of the reduce task. In the event that the master does need to reschedule a task to some other worker, then the master will update the records on the corresponding nodes. For instance, if a map task fails while it's executing, the master node will need to update the records for the corresponding reduced tasks so that they access the correct intermediate data. We do assume that master failure is uncommon, and this makes sense because we only have one master node. However, it's easy to extend the MapReduce programming model to support master failure by simply using a checkpointing system, and this would allow us to continue executing successfully even in the event of the master node failing. Let's see. So to gracefully handle node failure like this, we need to make a few assumptions about the underlying file system as well as assert a few assumptions about the output in the event of a node failure. So even in the event of a node failure, we do maintain causal consistency under the MapReduce model. This means that although we cannot guarantee the exact ordering of tasks on the map or reduce nodes specifically, we can guarantee that anytime a reduce node executes the reduce function, that the corresponding map task has completed successfully and given the correct output. This likewise relies on the map and reduce functions being able to atomically commit their output to the underlying file system. For example, let's say the master node incorrectly diagnoses some worker node that's running a map task as failed. Then in that case, the master node will reallocate the same map task to some other node, and it may be the case that these two worker nodes will commit to the same file at the same time. And we need to know that the underlying file system can handle this and still give us some correct output. And so that relies on the atomic file renaming of the underlying system, the Google file system. And that is explained in more detail in some of their other papers. Likewise, one key optimization that the authors point out in this paper is that of locality. Specifically, as I had said before, the master node, whenever possible, will schedule corresponding map and reduce tasks on the same node so that intermediate data can be read locally rather than across the network. And this is based on the assumption that network bandwidth is extremely scarce in their cluster, and that definitely becomes a reality when you're dealing with the number of machines and the type of commodity hardware that Google uses. So this actually does conserve quite a bit of bandwidth by using this locality principle. It's unclear, however, how much of this optimization is done using the MapReduce model itself through the worker node, or through the master node rather, and how much is actually done using the underlying Google file system. Because we do know that the Google file system transparently distributes files based on locality and handles replicas as well transparently for backup purposes. However, their scheduling algorithm in the MapReduce model does aim for locality and optimize for this, and we know that as a result, most of the reads happen locally, meaning that the optimization does work, and most of the time the master node is actually able to schedule map and reduce tasks to happen on the same worker node and only read intermediate data locally. To talk about the division of tasks between the map and reduce phase, let's define M to be the number of pieces that need to be worked on from the map execution, and R to be the number of pieces for reduce execution. The authors do point out that their MapReduce model works best when there are many more pieces than workers. In general, this means that for the map phase there are many more, that M is much larger than the number of nodes performing map execution, and likewise for the reduce phase. For the master node, we also show that this can be done efficiently even for very large systems. In particular, the master node only needs to make big O of M plus R scheduling decisions, linear time over the total number of pieces for the map and reduce tasks. This assumes that there is some constant multiple or some constant percentage of the number of nodes that are going to fail. In the worst case, I suppose we could have that all of the nodes fail and that it's big O of the number of nodes in their system because they keep having to allocate new nodes. But in practice, it turns out to be about linear time. Likewise, we can show that the state that needs to be stored at the master node is only big O of M times R, but this is typically only around 1 byte per MapReduce pair. So it just turns out to be about a few kilobytes of memory that needs to be stored in practice. Another interesting optimization that the authors of the paper propose is to do backups. And this means not in terms of data, but actually in terms of doing duplicate work for some of the tasks. The problem is that there are always some stragglers, particularly in MapReduce tasks that have many different tasks running in parallel. This can be caused by unusually slow machines, typically from resource competition such as for disk or network I/O. Their solution is to actually relaunch a small number of the slowest tasks and run them in parallel. That way, whichever of each pair of tasks complete first, we know will give us some valid output for the final output of the entire MapReduce application. They empirically determined this to be only about less than 5% of the total tasks, but this can reduce the total execution time by over 40%. To allow finer grained control over the MapReduce model, the library also exposes several key functions to the user that they may override. For example, the partitioning function, which helps allocate work to each individual worker node, may be overridden by the user if they want to control how the workload is actually divided between all of the nodes. For example, suppose we were doing a simple word count application based on the content of URLs. So we could actually set up the partitioning function such that all of the URLs with the same root host are processed in the same execution of a reduce function. And this could be used for any number of reasons, for instance, something with PageRank, perhaps. Likewise, we could guarantee some ordering for the order in which the intermediate key value pairs are processed, perhaps increasing key order, and I believe that's actually the default in their in-house implementation. Likewise, we could define a custom combiner function. And this would be an optional step between the map and reduce functions that would allow simplification, some pre-processing of the output of the map function that would help clean up the input to the reduce function. So a perfect example of this would be with something like a word count application like we described before. Perhaps we aren't interested in common words like the words the. That might occur many times and would slow down our computation drastically. So this would be a perfect example of a combiner function to go through and strip out common words. Likewise, we may want to skip certain records depending on our application. For instance, if our application does not need to have every single document processed to get an approximate word count for some search, then we might just want to skip documents that are causing the system to slow down. But in particular, one example they give is that the master may skip certain records that continue to make worker nodes fail. Likewise, we can expose some status information on the MapReduce computation as a whole from the master node. We can also provide hooks for executing this entire MapReduce operation on some local machine for debugging. And we can even expose counters for certain global events that happen in the map or reduce executions. For example, to the right you can see an extension of our word count example from before, except where we're going to increment a counter every time we see an uppercase word. Alright, now we're going to get into the performance analysis that Google presents in their paper. Specifically, they do an analysis on two example programs. You should note that they measure I/O as an approximation for the amount of time it takes the entire MapReduce operation to complete, and they do this because it is such a scarce resource in their system. The cluster consists of 1800 2 GHz Intel Xeon processors with hyperthreading enabled. Each of these has 4 GB of memory, 2 160 GB IDE disks in RAID, and a gigabit Ethernet. The example programs are first a grep for a particularly rare pattern. Specifically, it greps across 10 to the 10 100-byte records. It's about 1 terabyte of data, and only has about 100,000 hits. Likewise, a large sort benchmark is the other one, based on the TerraSort benchmark. Is also 1 terabyte or 10 to the 10 100-byte records. You should note that the grep, we're simply looking at the total time that it takes for the entire MapReduce process, whereas in the sort we'll actually be looking at also the effect of running duplicate tasks towards the end of the MapReduce computation, as well as looking at the effect of killing several of the worker nodes in the middle of the computation. So let's start with a more basic experiment, the grep experiment. This had a particularly large input set to the map computation, a particularly small output of the reduce computation. Many input files, around 15,000 input records, but only one output file. Overall, the computation peaked at 1,764 machines in use, and at that point in time we had 30 gigabytes per second of transfer speeds. The whole computation took 150 seconds in total, but more than a minute of that was setup time, and this was accounted for by Google File System opening more than 1,000 input files at the beginning. And on the graph to the right we can actually see the transfer speed versus time. We can see that the whole computation did actually only take about 80 seconds once the Google File System had opened all of the input files. On the other hand, the authors present a much more interesting analysis of the larger sorting experiment. Specifically, they look at custom partitioning, they try turning off backups to avoid stragglers, and they actually induce 200 machine failures. Overall, the authors show that in normal execution, the entire application only takes about 850 seconds. Without any backup tasks, however, that skyrockets to 1300 seconds, and with 200 machine-induced failures, only around 930 seconds. So it's a relatively small increase of 80 seconds inducing these failures. On this slide, we can see a much more in-depth analysis of the performance of the sorting experiment. On the top row, you can see the input transfer speeds, which is primarily the transfer speeds from the input files into the map phase. And you can see that the map phase occurs from around 0 seconds to around 200 seconds on the graph. Likewise, on the second row, you can see the shuffle speeds, the transfer speeds, and these are actually the transfer speeds of data transmitting from the end of the map phase to the beginning of the reduce phase. And we can see that this begins somewhere around 30 seconds into the computation. So actually, as soon as the first map stages start completing, the data starts getting transferred over to the corresponding worker nodes to do the reduce stage. Finally, on the bottom row, we can see the output transfer speeds. And you can see that this this is primarily from the reduce phase, and this happens from around 200 seconds to around 850 seconds in the normal execution. And the normal execution is shown in the far left column. The execution for the same application but without any backup tasks is shown in the middle column, and then on the far right column we can see the time required for normal execution when 200 tasks are killed around 300 seconds into the computation. As you can see in the middle column, the no backup tasks actually had a tremendous effect on the total time to complete the operation. You can see that although the curvature of the transfer speeds appears to be almost exactly the same as the far left column, there appears to be a very long tail at the end of the output phase because the entire computation doesn't finish until 1300 seconds in. And this is exactly the problem that the backup tasks were introduced to fix. In the far right column, we can see that from the interesting anomalies in the top two rows on the far right column, we can see the time when the 200 machines were actually intentionally failed. And that's around 200 to 300 seconds into the computation. And you can see that shortly thereafter, in the bottom right graph, you can see a dip in the speed, in output speed, and that's representative of that gap while everything's getting back to speed. But you can see that the computation still finishes around 900 seconds, so it actually does recover pretty well, considering that around 10% of all of the machines being used fail at the same time. So to summarize the findings from these graphs, we can essentially say that the backups were very similar to the normal execution pattern and had relatively minimal overhead in terms of the total amount of computation time. All but 5 of the tasks finished in 960 seconds, and without the backups, to finish the entire execution required 1,283 seconds, which means that the last 5 tasks took 30% of the total execution time, or it was 44% slower without these backups included. On the other hand, we can see that inducing 200 machine failures, even though we did kill over 10% of all of the workers being used, and all at the same time, you can see that the effect on the graph between 200 and 300 seconds, re-execution does begin immediately, and it actually only results in a total of 5% increase in the total execution time. From here, the authors move on to talk about its dramatic impact since its advent in February 2003. It's had a tremendous improvement in the reusability of much of the code at Google. It's simplified many of the applications that worked over the cloud and has been applicable to a large number of applications on the cloud. As you can see, they've used it for web search indexing, large-scale machine learning problems, presumably for advertising and personalization, large clustering problems, query trend analysis, large-scale graph computations, presumably for something like PageRank, and web crawling and analysis, and any slew of other applications they haven't disclosed. On the far right, you can see the exponential-looking graph from 2003, in March 2003. You can see that grew from only around a handful of users in middle of 2003 to nearly 1,000 instances in the Google Codebase near the end of 2004, and that's just in the first year. And you can see more details about the magnitude of its impact in the bottom right corner, and just the amount of time that it's actually being used. Obviously, MapReduce is not the first of its kind in terms of restricted programming models for parallelization, but the authors do argue that MapReduce is simplified and distilled based on real experiences at Google, and this is one of the things that sets them apart from other related work in the area. Their abstraction allows them to do interesting things like automatic fault tolerance, parallelization, and load balancing, whereas other abstractions such as bulk synchronous programming and MPI of the time were too high level to provide actual the same services of fault tolerance and parallelization. On the other hand, their locality optimizations and backup tasks optimizations were both derived from other similar work such as active disks and the eager scheduling algorithms in the Charlotte system. Likewise, the work in sorting with MapReduce is very similar to the work with NowSort at that time. And likewise, dynamic scheduling is very similar to the work with River around that time, but where River carefully scheduled disk and network transfers to help load balance, MapReduce instead takes a more restricted model and then uses fine-grained tasks to allow redundant execution of tasks for dynamic scheduling. In terms of BADFS, which is probably the closest comparison to MapReduce of that time, BADFS was actually different because it targeted wide area networks, but it did have similarities in terms of redundant execution and the locality-based scheduling approach that MapReduce introduces. In a nutshell, MapReduce is a programming model geared towards parallelization. Specifically, MapReduce introduces a restricted model that allows it to automatically provide fault tolerance, transparent parallelization, and load balancing to the user. Obviously, this was extremely easy to use, as you can see by its interface as shown through this presentation. It's applicable to a wide variety of cloud-based applications, distributed applications, and it's extremely scalable, as evidenced by its use in the large data sets at Google. In terms of novelty at its time, the authors were actually able to show that using MapReduce that a restricted programming model can allow a more robust system. This was evidenced through the fault tolerance, parallelization, and load balancing that MapReduce could provide because of its restricted model. Likewise, they showed that network bandwidth is an extremely scarce resource and actually used transfer speeds, specifically the network bandwidth, to gauge the performance of their system. And finally, they show that redundant execution can alleviate failure or straggler problems by using MapReduce's more fine-grained task structure. So that's all. Thanks for watching. If you have any questions or comments, please use the wiki below.